Welcome, Michael at Wickerson Studios, continuing this fairly slow start on the definitions of the elements in Book 1 of Euclid's Elements. Should be pretty good. Fundamentals of plane geometry involving straight lines. I did 10 on the last one, and I've done the next 10, and there's only 23 definitions, so we'll be done this one more short GHZ file. So I'm just kind of getting my hand accustomed to, in very simple ways, GH2, playing with a few metas, doing things like that. But what I'm going to do is just turn this one off and take you back to definition 11. Couldn't be easier. So just, I probably overcomplicated it to be sure, but let's just initiate the first one. And I've written in the definition, an obtuse angle is one greater than a right angle. So I wrote in a system of a circle. I usually don't bother making this kind of, if it's just scalable, I kind of hard-code it in, because what does it matter? Keep things to 1, keep things small models just to start. I do like this pi through rotations. I'm actually rotating through 2 things. Evaluating curve at 2 points. I thought that was a nice little technique. Instead of taking it and mirroring the point, evaluating 1, I thought I'd just evaluate at a local pi and 2 pi. Which is nice to think about. It's a faster way to do it. I don't do it every time. And then I thought I'd try my hand at some of the paths and lists from paths and just get a sense of this. So grabbing your tree, it's a very fast dispatch, but it also gets your head into what's happening when you're dealing in paths and sites and lists. And so I'm just going to try and do that a little more as models get more and more complicated. And then I have a evaluate curve multiplied by a number here that I can actually pull it up from 90 degrees all the way over to 180, which basically builds that obtuse angle if you look from 90 degrees to 180, which is at the center point down here. So I haven't labeled anything because it slows things down, but it's a nice little triangle. And then what else did I do? I had a point here for some reason. I couldn't tell you why. That point's there. Probably shouldn't reference that point from that. I should come back and reference it from here. Like I said, my scripts sometimes get a little clumsy to start. That's why I put it in here to influence the next one, but I could always relay. Nice little technique here is to take your relay, and I like it. It's in param, so it's over here. You just grab your relay and slap it in, and then you can take that relay and run that down to whatever you want. So relays can be messy, or they can be clean, but they make one script dependent on the next one, and you don't have to double up your imagery. So this doesn't have to be way over here, but it is a multiplier for taking it from pi over 2 back to pi, 2 pi or 0, or no pi, I guess you'd call it. Anyway, I had a multiplier over here I was going to do something with. Doesn't look like I was doing anything with that. This one was going somewhere, which ended up being an amplitude. I never ended up using any of this stuff, except that might have been driving my next geometry. But it looks like I'm just cleaning up my script now. And sometimes pulling these things back out, you can see what you were actually doing. So pretty simple script. But I did like the fact that I was going in and using a little bit of paths and tree data from the data. So try and get your head into lists, trees, and some of these filters a little deeper. And if you can, try your hand at metas. So the next one is just the exact same thing, because definition 12 is doing the exact same thing, and that's why I slid this down here. You can see that if I'm going to produce an obtuse angle, it's obvious that I'm going to produce an acute angle at the same time, which is this one up here. And like I said, I could label it ABC if I wanted to, but you can see that changes its angle all the way along. And I could have had it come to the other side of the circle too, just to build it, but I thought this was a nice little model for this. Anyway, that's it. If we continue, we can actually get into 13, the boundary, which is the extreme. So I just took the boundary of the triangle, and I used an old Grasshopper 1 deconstruct BREP to produce some curves. You can see you have 3 closed curves, which act as the boundaries. Not too difficult. So once I'm done that, I kind of use this point. And I like this kind of shutting off the scripts from the source, and then everything else goes invisible. I think that's a really nice technique. It's different that people might not like off the start. So a figure is that which is contained by some boundaries. So let's take the next one, very similar to what we just did. And I just thought I'd take a point, make a circle, produce a bounding rectangle, and a triangle from 3 points, all of these being made. They don't have to you know, you can play around with the scale of those. And I thought it would be fun to just pull those into surface from disk, surface from rectangle, surface from triangle, which produces surfaces because that's the main point of it. A figure is that which is contained by some boundary or boundaries. And then you can just change the side. And I thought for fun, why not throw in the subdivisions, what happens to a circle, a square, a rectangle, and a triangle when you subdivide it. And you'll just have to kind of click on those to see what those things are different. And some are overlaid. I'm not sure if you can move things forward or back in this to bring them to the foreground, but the subdivisions certainly come to the top. So you can see those pretty nicely. Actually, not the triangle one. I guess it has to do with the order. Anyway, all right, so let's move right along. 23 definitions. 15 is a circle, is a plane figure contained by a line. A single line, which is called the circumference. So that's pretty easy. Let me take off this data here. Let's put on the next one, which is fairly easy, and see what our script does. There it is. Is called the circumference. And I actually did that by just taking a point, making a circle, and then pulling it out. What did I do to show the circumference? I think I wanted to show evidence of, yeah, this one here. Just grab the point, put it into a circle, and even though I moved this stuff down here for now, it doesn't have to be there, but it kind of proves the next part of the script. The next definition. But you can see that just multiplying that by pi, you're going to end up getting pi, which is the circumference, which is familiar to anybody with a unit 1 radius circle. And what was the second part of that? Such that all straight lines radiating towards the circumference from one point amongst those lying inside the figure are equal to one another. So then I just took the circle and divided it into as many count as I want. And in doing so, I produced these lines that act as radii. Of course, that's about it. And those lines can be looked at, and you can see that the lengths are all exactly the same as 1. So basically, it's just kind of a definition of a circle. Then definition 16 is the point is called the center of the circle. So I grab my circle and I do an area, circle check center, and I get 0, 0, 0, and I end up with a point right in the middle, which I guess I can put a little red dot on there. And then, well, I think it's, once you start layering these things, it's hard to, when they're coincident, to get the metas to work. Just something to think about. 17 is pretty nice. The diameter of a circle is any straight line being drawn through the center and terminating in each direction by the circumference of the circle, and any such straight line also cuts the circle in half. So what I did there was I grabbed the circle here, and there it is. I guess I can turn this one off. There we go. I probably could turn off the other points that weren't necessary. I'm only relying on the point of that circle right here, this point, and the circle being this one that we made in the last definition. And I've done a closed curve point analysis and world YZ mirror. That's another way of making 2 points, the one here on this side mirroring through the center. And that's kind of the way that I didn't do in the first script. If you remember back, I was actually going in and I was saying, okay, let's evaluate it at pi 1 and 2 instead of doing the mirroring. So it's all up to you to what makes you comfortable and what you want to do. And either way, I'm going to produce a line which is the diameter from here to here. With the metas, you can see it. And then I'm rotating that through the same pi. I can take that curve and I can rotate that. Now you'll notice very carefully that I don't rotate it beyond 1 to 2 pi. Because I don't put it exactly at 1 and I don't put it exactly at 2. And the reason I do that is because there's this weird thing that I noticed in robotics happens, but also with this is that line can flip. And if that line flips, it makes this definition not work so well. So I'm going to go into here, I'm going to turn this point on, and probably crash my computer because I did something. And I'll send my crash report into Rhino if that's what happened. Sometimes it can survive a crash report, sometimes not. But let's read this until it crashes. And a semicircle is a figure contained by the diameter of a semicircle. The center of the semicircle is the same point. And the center of the semicircle is the same point as the center of the circle. Well, that's pretty easy to prove, but I think I wanted to go on and show more than that it could be cut in half. And so there was something in here that I left out. Yeah, the circle cut off by it. Maybe I didn't read 18 exactly right. Let me take a look at this. Oh, We did hit pause there for a minute. So I was coming down here, and I think that's exactly what I did. Let's enable the circle. There it is. So 18 is actually a semicircle is a figure contained by the diameter of a circle cut off by it. And the center of the semicircle is the same point at the center of the circle. I think 17 was actually what I was supposed to write here. Straight line terminators. Well, yeah, this was it. Any such straight line cuts the circle in half, which is why I took that extreme down to here, but I actually pulled this one in. It does the same thing for 18 and 17. The sample here was that you could see that any circle, as I rotate it, like I said, if I go all the way to 1 to 2, then this line, the diameter flips, and these get an awkward area. But I'm trying to prove that the area value of both halves, by pulling it through a shatter and a dispatch instead of using the paths that I was doing above, you can see the loft from the top and you can see the loft from the bottom and see that the areas are close enough. And actually, when you put them on here, they'll round up to pi. But like anything in computers, you can't get perfect pure math on what you're doing. And I also put this one in, the same model in, just to say the center point right here is the center of the circle. So I think two things were proven in this model. Definition 17 and definition 18. Hopefully I can continue. I know I get cut off there for a bit. And then I can kind of leave all this as we finish up, which is fairly smooth. Take this one, disable it. And I'm going to go back down to here. 19's kind of long, but it really means something fairly simple. And I can use a very simple diagram to do that. You can see that this square, because of 4 sides, can become 5 sides, can become 3 sides. And basically, it's the rectilinear structure, as long as it's planar, are those figures contained with straight lines, so straight lines that are on a plane, trilateral figures being those contained by 3, quadrilateral by 4, and multilateral by more than 4. So that's a pretty simple little diagram. Just take that one off. And then back into the smaller model, take a look at the last one, 20, which I find pretty interesting. Just grabbing a circle, finding a closest point. I'm using the mirror to get the diameter across here to get 2 points, and then evaluating those 2 endpoints. But then I'm finding the length of those points, and I'm making 2 circles. And this is really nice to play Euclidia on an online phone program, because you actually solve everything by lines and circles. So you can build all of your models out of that to design some very simple geometries. I'm using Grasshopper 1 curve to find a point, which will allow me to build a right angle triangle, and actually it generates in both directions to solve both solutions, which is nice. And I've actually, it doesn't say equilateral because of the estimations that one maybe isn't exactly right. So you can't really do that, but it is an equilateral triangle close enough to it. The next one you could actually play with, that's the meta that I'm playing with, but you can actually play with the heights of the isosceles triangle in red, this one. So there's the isosceles triangle in red. And then you can actually go down, and I used a little bit of pi by just this one round circle on the right. Now you could always do the one on the left to make your obtuse triangle. Now it stays isosceles because I'm doing it, and it's kind of creeping around. It shouldn't be isosceles. I guess it's called isosceles. That's just the name of it. But 2 of the angles are not. It's when all 3 angles are different. So at some point, some of these angles, I guess, could be right there, the same. They're kind of hovering on the same around like this. You're getting this kind of isosceles all the way through, which is not what I want. I actually want every angle to be different. So if I want to actually solve this script and say that a scalene triangle has 3 angles, I'm going to have to grab another point. And I think what I'll grab, just to make that work, because that's not solving the equation, these 2, I can always take this 3rd point with a quick little relay. So it's very playful. I mean, there aren't any right answers or wrong answers to what you're doing. That's not what I wanted to do. Well, there's wrong answers, but there's so many different ways of figuring it out. There we go. Don't know if that's the one I want, because that was the move. This one, I'm interested in how that's moving. There we go. I am starting to finally build a Yes, Scalene Triangle by doing that. So I think I'll change the model that way. So you got red, green, and blue as you go. It's pretty nice. And your red one's there. And this one, you can't see the red one because it overpowered it, but that's just the way the green went. Yeah, so I'm finding out what colors kind of have priority over others, but that's a good way to make some nice scaling triangles. And just fixed it as I go. And now I'm going to work on just the last 21, 22, 23 of the definitions, and then we will get hard into the postulates and see where that ends up going in common notions. Thanks for watching.